Okay, welcome back to lecture 18.3, where we're going to talk about the importance of isolated systems, or isolated versus non-isolated systems. Okay, remember last time we discussed the scenario where we might go from a state A to a state B, and you could imagine going there through some irreversible process and then coming back through some reversible process. Okay? So, we pointed out that if we had an isolated system, then dq was 0, and we said then we would have 0 was less than SB minus SA, and so SB is greater than SA. Okay, so why is it important to think about this in terms of an isolated system, right? We've got this dq that says we were isolated. That meant we went from A to B, and now we want to go back from B to A, right? So if A to B was irreversible, can we go back B to A along a reversible path? Okay, so I want you to ponder this for a second. Even pause if you need to, and stop and think about this. It's kind of a really tricky concept, really funny thing to think about. I've told you can go from A to B, but it's irreversible. I told you can go from B to A, it's reversible. But now I've imposed that this is an isolated system. Mathematically, that told us that the entropy of state B was higher than the entropy of state A. And so now I want to know, can I do this? If I did this from A to B irreversibly, can I go back from B to A? And the answer is no. This is actually impossible, right? Because the entropy of state A then would be lower than B, and there would be decrease in the entropy in a process. So you cannot go backwards. You cannot return to state A, not for an isolated system. Okay? Now, I mean, it's even right there in the name. It was irreversible. We did something irreversible to our system, and we can't get it back. The only way we can get it back, the only way to go back from B to A is to connect to another system. Right? We have to make our system not isolated. Right? We would have to unisolate our system to do that. Okay? Okay, so another way we can say this is that delta S is always greater than equal to 0 for an isolated system. And again, the equal only for reversible processes. If it's reversible, I can go back and forth, and if it's irreversible, I can't, right? Because the entropy increased. And the entropy always has to increase in any process. Okay, now, we have to be careful when we think about this, right? Now, there's a nice section in your book. So in Fin, this is chapter 5.5. In Fin. And then this is figure, it's related to figure 5.6. Okay? So let's imagine drawing figure 5.6. So what it was that I had two objects, one object A and one object B. And together they make my system, and I make nice adiabatic isolated walls. Okay? Imagine that A is at a higher temperature than B, and heat flows out, right? Okay, so what would happen if I looked at A? So if I were to look at what happened to A, then we would say, oh, well, ds, was something like dq over t, right? So my change for state A, right, for object A, let's say, should be that heat's flowing out. So I would expect heat's flowing out. This is now going to be a negative sign, right? My entropy of my object A has gone down. And that's true. The entropy of A decreased. But that wasn't your system, right? Your system was this everything, right? So this was all your system. And we had to look at what happened to B instead. So SB was greater than 0, right? The heat went up. And if this were a reversible process, then so if reversible, then SA would be equal to SB. But if irreversible, which seems likely in this scenario, then the entropy of B would have been greater than the entropy of A, right? So that is, this may have decreased during this process, but this increased even more. And so my total system entropy always increased. So this brings up a really interesting point, which is sometimes my system is very large, right? Sometimes you can think about doing a process, for example, in the room, or as a power plant, or as Earth, right? And sometimes you realize that, for an isolated system, for a reversible process for an isolated system, the entropy is going to be 0. But sometimes my whole system is the universe, right? Sometimes my system is the whole entire universe. That's my isolated system, right? Sometimes the only isolated system I can think of is my entire universe. The laws of thermodynamics still have to hold for the entire universe. And so the answer is that exactly the same, right? That is, the entropy of the universe, when you think of it as an isolated system, is always going to be increasing for any irreversible process. That's really interesting to think about, right? And this sort of, continues with this idea of time's arrow, right? That the universe, the time in the universe, the whole idea of time, the whole idea of what we see as time, is really that the process, that every single process there, when you consider the whole universe, the entropy in total is going up. Quite interesting to think about, right? Okay, so I think that this is going to have very, important consequences in the long-term fate of the universe. We can talk more about that class. Okay, so now changing topics just slightly. So sometimes we have to, it's important to consider our process. Okay, so it's important to consider our process, and sometimes we have processes which seem like they're out of equilibrium. So in figure 5.8 gives a good example of this. So in this section, they discuss how, I think it's really worth reading. Imagine again an isolated system. Now instead of having two objects, A and B, imagine one object, one bar, which is hot on one side and cold on the other side. Here in this case, because we think of it as a thermal gradient, this system is not in equilibrium, right? And so we can't describe this via some process which allows us to calculate this, right? And so instead, what your book says is you can do is imagine dividing that up into a whole bunch of objects, slice that bar into a whole bunch of sections, right? Where the left one is still hot and the right one is still cold, but you have incremental temperature differences between them. Now we can think about this thing as kind of quasi-static and equilibrium, and we can do the problem. So that's an important example. So you might as well take, in this case, the one that you can do the example for, right? So when you can do the if there is a way to take your system that isn't in equilibrium, and like when we did throttling, right? It wasn't in equilibrium, but we could come up with a scenario to make it in equilibrium, quasi-static. Then we could do the problem. Same thing for a thing like this. You can calculate the entropy that way. So what we're going to do now, but I want to reserve it for class, is an example where we're going to do some processes. So examples in class where we're going to calculate the entropy and the entropy changes if we do some various processes, okay? So we're going to take and imagine doing some processes with an ideal gas, okay? So we're gonna heat. We're gonna heat and expand ideal gases and calculate the entropy. Okay, so we'll do these examples in class. We're going to do it for some various processes when we'll see the equivalence of these processes. Okay, all right. So that's what we're going to do. There's actually it's quite a long example. We'll do that in class. Okay, so we'll reserve that for class time. So I'll see you in class.